Today we are going to learn how to convert a galvanometer into a voltmeter. So this is our galvanometer. For this galvanometer we had already calculated the figure of merit and the resistance. The figure of merit for this galvanometer, already done in a previous experiment, was 21 microamperes per division. So we can find out the current, the full-scale deflection current. How many divisions we have here? We have 30 divisions, and we can find out the full-scale deflection current for this galvanometer. So for a galvanometer, the figure of merit is 21 microamperes per division. So we can calculate the full-scale deflection current, that is the figure of merit times the number of divisions, and here we have 30 divisions. And if we multiply these two, we get 630 microamperes. So this much current is required to produce a full-scale deflection in our galvanometer. We can convert this into milliamperes. So this is 0.63 milliamperes. This is the full-scale deflection. A galvanometer can also be used to measure the voltage. A galvanometer is a versatile device. We can use it to measure current, we can use it to measure voltage, temperature, speed, anything. How does it measure voltage? It is also a voltmeter. But of course it will measure, because the full-scale deflection current is very small. Therefore the voltage that is required to produce full-scale deflection is very small. We can find out, if somebody asks, what's the maximum voltage that this galvanometer can measure. That we can find out the maximum voltage that the galvanometer can measure, that Vg we could write, would simply be the Ig times the, and this is the current times the resistance of the galvanometer. Now, if we know Ig is 0.63 milliamperes, and G for this galvanometer is 66 ohms. So when we multiply these two, what do we get? So 66 times 0.63, and we're getting 41.58. This is 41.58 millivolts. It's approximately 41.6 millivolts. But of course we don't want to measure this. Actually what we want to do in this experiment is we want to convert this galvanometer into a proper voltmeter, a voltmeter like this. Now I'm using the top scale. This is a voltmeter that measures a maximum of 1 volt. Okay, a maximum of 1 volt. Just now we saw that this galvanometer can measure a maximum of only 41.6 millivolts. So we need to convert this galvanometer, which can measure a maximum of 41.6 millivolts, into a voltmeter that can measure a maximum up to 1 volt. Okay, we're using the top scale because we have put the toggle switch at 1 volt. This voltmeter has another option. We could also use the 10 volt scale. We could use a 10 volt voltmeter. We need to put the toggle switch down. But in this case, we're keeping it up. Okay, we want to measure, we want to convert this galvanometer into a voltmeter that measures a maximum up to 1 volt. How do we go about that? Let's see. Okay, this is our galvanometer. It has some resistance, we know 66 ohms. This part is our galvanometer. Now, this can handle only a maximum of 41.6 millivolts. So we need this galvanometer to handle more voltage. The voltage drop across this at maximum is 41.6 or approximately 42 millivolts. But if we want to measure up to 1 volt, we need to attach a series resistance. Okay, let us call that R. And this whole thing then becomes a voltmeter. So this part here, when you attach a series resistance to the galvanometer, becomes a voltmeter. And now this voltmeter should be able to measure the maximum voltage V, and that maximum voltage has to be 1 volt. We could also write 1 volt as 1000 millivolt, just for the sake of calculation. Okay. Now, if we use the Kirchhoff's law to find out the relation between V, I, and G and R, we could clearly see that the voltage across the voltmeter is simply the current through the voltmeter times the resistance is now G plus R. We need to evaluate for R. So this is V by IG minus G, that is equal to R. So this is our formula for calculating the series resistance that we need to attach to this galvanometer to convert it into a voltmeter. Okay? So in our case, how much is the series resistance? Let us calculate. So R is equal to 1 volt. Instead of 1 volt, we'll be writing 1000 millivolts divided by IG. The full-scale deflection current for our galvanometer, we have already calculated that. That is 0.63 milliamperes minus the resistance of the galvanometer, that is 66 ohms. So this milli and milli cancels out. Let us solve it. How much is that on a calculator? So we have 1000 divided by 0.63. And we're getting this much, and we're subtracting 66 from it. So we're getting 1521.3. So the the resistance, series resistance is 1521.3 ohms, which is approximately 1521 ohms. So what we need to do is, to our galvanometer, we need to attach this much resistance so as to convert the arrangement into a voltmeter that measures a maximum of 1 volt. Okay, let us do that here in experiment. Okay, this is our galvanometer. Now I have attached a series resistance to it. Okay, this is the this series resistance I will obtain using this resistance box. Okay, so how much resistance do I need? I need 1521 ohms. So I have taken out, see, how much is this? This is 1000. 1000 plus 500 is 1500. 1500 and this is 20, 1520 and 1. This is 1521 ohms. 1521 ohms I have attached to this galvanometer. I have attached this series resistance of 1521 ohms in series to it, and this whole thing now, this from this end to this end, now becomes a voltmeter. This part is a galvanometer only. Now these two together, the series resistance and the galvanometer together form a voltmeter. Okay, so I claim that this galvanometer has now been converted into this type of voltmeter. But hold on, I need to test that claim, and that is what is important in this experiment. We need to verify how we are able to convert the galvanometer into the desired voltmeter. So for that, we need some verification circuit. How will we verify it? What we can do is we could arrange a variable battery, maybe using a potentiometer, a variable power supply. We could attach a variable power supply and attach 2 voltmeters to it. Okay, variable power supply, and attach 2 voltmeters to it. So this is our this is the voltmeter, the actual voltmeter, and we will attach in parallel the galvanometer, which has been converted into a voltmeter. Okay, this is our galvanometer converted into a voltmeter. So whatever voltage we apply here, this voltmeter will read that voltage, and so will this. These two are arranged in parallel. Whatever voltage is measured by this voltmeter is also measured by this converted voltmeter. Converted galvanometer. Okay? So this is the circuit we are going to use, and I have arranged the circuit likewise. So you could see this is our this is the power supply that will be using. This is the potentiometer. I will increase the voltage across this voltmeter, and to this voltmeter I have attached in parallel to this voltmeter now, the converted galvanometer. You see the positive end of this goes to the positive end, and the negative end, negative ends are connected here, okay, to this. You can check here, say if it's the positive end, negative end, the positive end and the negative ends of the 2 voltmeters are connected together, and they are connected to the variable power supply. Okay, now I will be increasing the voltage over here, and the voltage will show an increase in this voltmeter as well as this. So when we have to verify, how do we verify? We make a table for different readings. We'll take different readings, 1, 2, 3, so on, and this is we'll see how many divisions. We'll see converted galvanometer reading. We'll see the actual voltmeter reading, actual voltage, and then we'll also find the percentage error. If there is some error. In the previous experiment, when we converted this galvanometer into an ammeter, we found that there is no error. Actually, there is some error, but it was not detectable. The error was very small. Let us see if we can detect an error this time when we convert the same galvanometer into a voltmeter. So before we do that, before we find out how do we measure the reading of the converted galvanometer, so what we need to do is we need to give meaning to each division of this galvanometer. We claim that this now is a voltmeter, but we need to give meaning to these divisions. Previously, the galvanometer had no meaning. What does this 10 mean? How much is this 10? How much voltage it measures, how much current it represents. So how do we give meaning to that? That's simple. Now, if I'm claiming that this voltmeter is the same as this voltmeter, then the full scale deflection, that is 30 divisions, would correspond to a full scale deflection of this voltmeter. That would be 1 volt. So that means I could use a conversion factor. How can I find that conversion factor? Is simply 30 divisions of the galvanometer would mean 1 volt. So 1 division means 1 divided by 30 volts. Okay, so which simply means if you have, like, say 3 divisions deflection on a galvanometer would represent a voltage of 0.1 by 10, that is 0.1 volts. and 6 division deflection would represent 0.2 volts. 9 division deflection would represent 0.3 volts, and 12 division deflection would represent 0.4 volts, and 15 division deflection would represent 0.5 volts, so on. Okay, so this conversion factor we are going to use to find out the reading of the converted voltmeter. We'll also see the actual voltage from the original voltmeter and then find out the percentage error. So let us start the experiment. I'll put on the switch. I'll increase the voltage here. Just a minute. So let me produce first a deflection of 3 divisions, okay? This is 3 divisions deflection, and how much voltage are we reading? Clearly, this is 0 volts, this is 0.2 volts, and this is at the center. This is 0.1 volts, say 5 division deflection, okay? So, in this case, okay, this is at the center, this is 0, and this is 0.2 volts, so this is 0.1 volts. So what is this showing? 3 division deflection. So 3 division deflection, this is 3 divisions, and that 3 divisions corresponds to 0.1 volts. The actual voltmeter is also showing 0.1 volts, so no error detected. Okay, very good. Let's take another reading. Let's increase the deflection to 6 divisions. Just a little shy. So this is 6 division deflection. You can see there is some parallax between my cell phone and the galvanometer. 6 division deflection, and how much is this showing? You could see this is 0.2 volts. So 6 divisions here is equal to, this corresponds 0.2 volts, and the actual voltmeter is also showing 0.2 volts. So no error detected. Let's take the third reading. Let's take it to 9 divisions deflection. You can see there's some parallax between the cell phone's camera and this. This is the actual. This is 9 divisions deflection. And how much is this showing? And this is going towards the center. That's 3 volts, 0.3 volts. So clearly this is 9 divisions is 0.3 volts, and here we have also 0.3 volts. So voila, wonderful. This is, now we'll go for 12 division deflection. Let's see 12 divisions deflection. Sorry, here. 12 division deflection would be, oh, this is too much. Just 1 minute. So this is about 12 divisions deflection, and how much is this showing? 0.4 volts. So 12 divisions is 0.4 volts, so this is also 0.4 volts. No error detected, and we can take a 5th reading for 15 divisions, which corresponds to 0.5 volts, which should be 0.5 volts. Let's see the actual voltmeter, what it is showing. First we'll set up this at 15 division deflection. Why is there a parallax between this and this? You can see now there is some error here. We have this is 15 division deflection, and this is showing just a little over 0.5 volts, just a little over. This is 15 divisions deflection. How much is it showing? This is showing 1 division extra, and 1 division corresponds to 0.02, and 0.02 would mean, so this would be 0.52 volts. It's a very small error. You can calculate the percentage error in measuring 15.5 volts. You see, the higher the voltage you are trying to measure, the error accumulates up. There would be a small error, but it's undetectable. But as you go on increasing the voltage, every volt has some error that accumulates up, and this, it's showing the error accumulates up to 0.52 volts for 0.5 volts. Let's see what is the percentage error. This is 0.02 extra divided by 0.5. So this is only 4%. We are only getting a 4% error. Okay? So clearly up to this 15 volts, we have almost no error in detecting the voltage. But as we go beyond 15 divisions to 30 divisions, then the error accumulates up. Okay, there would be some error. Okay, this is a fine, we got a very good reading, and you can copy this on your notebook, worthy of looking up. Okay, thank you.